Hey, welcome to the NCG and T seminar. Today's speaker is Valentina Guarin, and she's going to talk about Fedosov connections, L-infinity algebras associated with DG manifolds. Please.
Okay, thank you. And to break the ice, I have something to tell you. I found my wallet. So for those of you, you know that I lost it, and I found it today. It was in my room all this time, so it's embarrassing. Okay, so to start, I'm going to just give the definitions of L-infinity algebras, and I will try to explain the relation between this and Q-manifolds that he was talking about this before. So let me start with the definition. So to start with, I will pick a graded vector space. So let L be a graded vector space. It can be Z2 or Z-graded, as you wish. And let's consider the following operations. We will have some brackets. Let's consider some antisymmetric brackets. Let's take LK. I will take L copies of L. K copies, sorry. This. And I will have, in this definition, I will have these brackets as antisymmetric. Of course, graded antisymmetric, which is, it means that this graded antisymmetry, it just means that you have something like this. It's just -1 to the parities of V and W, and then we have this. So we have these antisymmetric brackets of degree 2 minus k. And we will have also, in addition, some relations between these brackets. I will try to make the connection between this definition and the definition that you gave in the last lecture in the course that you're giving, because you were making this definition in terms of co-derivations and coalgebras. So we will try to see how is this related with that concept. Okay, so now we will have the following identity, which is horrible, and I will just write it for completion, but I will explain what it means. So we have something like this. Okay. Okay, so by this notation, I mean a permutation of this n, how to say, Sn. It's just a permutation of this symmetric group. And we will have these relations. So how can I write this? Okay, so this identity that I wrote here is just called the generalized Jacobi identity. So if we just compute the first terms for n equals 0, 1, and 2, what we will have is that in the first case, we will obtain that L1 squared is 0. So this means that we have a differential. We have a differential, yes. So we can speak about cochain complex. So we can speak about cohomology. Secondly, we will obtain that the relation between L1 and L2 is that this is going to be a derivation with respect to the L2 bracket. So we have something like this. L1 of L2 of 2 elements is just going to be something like this. And here I will have a sign. It should be degree of B1. So as I told you before, this just means that this is a derivation with respect to the product. And the third identity, okay, maybe just here. The third identity that follows is that we will have something like Jacobi identity, but this is not precisely working. It means that the Jacobi identity will hold in the cohomology of the graded vector space. So I'm not going to write this, but what we can say from here is that an L-infinity algebra is giving you a DGLA in the cohomology. Okay. Okay. So now, what I want to say, yeah.
Not sure. So I can see how, so you have L squared thing.
Yeah.
In general, LK goes from K copies to L1. So then L1 goes from L1 to 0.
Yeah, L1 goes from L to L. This is K. And the degrees are 2 minus K. So in the first case, you have that L1 is of degree 1. So it's a derivation of degree 1. 2 minus K.
That's one copy. Yeah, yes, thank you.
Okay. So do you have more questions so far? Okay. So as I was telling you, this L-infinity algebra is giving you like a DGLA in cohomology. Okay. So now I want to try to see the relation between this and the concept of Q-manifold that we were seeing before. So I will try to see this graded vector space L as a Q-manifold, as a graded manifold. So how to do this? We just need to associate, we need to define what is the space of functions that we associate to some open set. So let's consider some point. So I will try to speak about formal pointed Q-manifold. So as Rudolf was saying, you have like a, how to say, underlying topological space. So in my case, I will have, let's consider a point. So I will speak about the origin here. I just have this point, and I need to associate an algebra of functions associated to this point. So what I do is that I just consider the following. So let me write something here, and I will explain later. Should be something like that. So what I'm doing here is that, you know that you can think about polynomials in a vector space. And the way to do this, like in a coordinate-free way, is just to consider the symmetric powers on the dual. So this is what I'm doing here. You can think that the algebra of functions are like polynomials on this vector space. And the shift, you may be asking why the shift. And it's because I would like the Q homological vector field to be of degree 1. So we need to make this adjustment to have this correct grading. So I will consider this algebra, and I need to define the homological vector field Q. So let's define the homological vector field Q. So I should have a derivation of these algebras. How can I define this? Okay, so let me think for a second. Okay, so here I was saying that these maps are antisymmetric brackets. And here we have the symmetric power, so we can just consider the same brackets that I had before, but considering this shifting. So this, what this is going to do is that it will turn the antisymmetric brackets into symmetric ones. So then we just do something like this. Let me try. How can I write this? Okay. Okay. Let me to define this derivation of these functions. I think it would be enough to define how is this vector field is acting on the generators of these symmetric powers. So we can consider some basis for L. So let's pick a basis. I don't know, E, A for L. And you consider like linear coordinates on the dual. You consider something like, I don't know, you can take coordinates corresponding to this basis, and then we denote by, it's typically denoted by this Z of A, which I think you were using this notation. I don't remember at the end. So we denote these coordinates, linear coordinates on L1. Now to define this homological vector field, I will just define it how it's acting on this coordinate, on this basic coordinate. And then we can just extend the action of Q by using the Leibniz rule because we want this to be a derivation. So I just need to define the action on this. Okay, we'll do it here. So I define this. I define this in this way. I have this formal expression. And probably it's just one. I will write the formula and I will explain what it means. Okay, so we have this. You see that I'm taking here the coefficients of the brackets that I had before. So what I do this, sorry, like where does this come from? I just, this is just defined as the action of these brackets on some basis. You take this basis that I wrote before, and you just evaluate this in the basis, and you have some coefficients. You plug it here, and you just define the Q field in this by this formula. So then you can prove.
The pair, for example, bracket this guy.
Again.
You take a pair this guy and both sides.
Okay, I'm here just evaluating, like in as is written before, you have these maps from L times L. I pick the basis and I plug it here, and then you have some coefficients. You will have some, you plug these vectors here in LK, and you produce a new vector. So you will have some coefficients with respect to this basis and the coordinates that I picked. And this is what I'm denoting by this, okay? So then you can prove, I'm not proving this here, I'm too lazy, and I think this talk is going to be sketchy. So you can prove that Q squared is 0. And this condition will be equivalent to this generalized Jacobi identity that we had before. So now there is some comment that I would like to make, and it's related to this course that you are giving. So you were, in the last lecture, you were giving the definition of L-infinity algebras, but you were using this language of coalgebras. So how to obtain this definition from here? You have, okay, let me try to see. Okay. So from these coefficients and from this expression that I have, you have some, how can I say this? Okay, let me try. By this formula, I'm decomposing this Q in many parts, like in some terms here, right? Some linear parts, some quadratic part, and so on. And this, each of these elements that appear here, they are acting in this way. They are taking the Sk symmetric power of L1 dual, and they are producing something here, right? So what you do is that you try to extend this. You try to extend this operation into the symmetric coalgebra here. And then you can prove that this Q that you construct here is a coderivation of this symmetric coalgebra. But okay, I'm not being very precise, but this can be thought as a coderivation, as you were saying in the lecture. Yeah. Mm-hmm. Yeah, yeah. Okay. What else am I going to say? Okay, this is just like some preliminaries. I would like to state the problem that I was trying to solve in my thesis. Maybe just before, I will make some additional comment, and is that sometimes you don't have this relation. Sometimes you don't have this differential here, but it happens that these identities can be modified to allow a zero bracket. So sometimes you have something of degree 0, and this is from the ground field to your vector space, and you have some relations between L0 and L1. So when you have the presence of this bracket, this is referred as a curve L-infinity algebra. This term is known as the curvature of the algebra. Okay, so now I think I'm ready to state the problem. Let me try to do it. Okay, where is the space? So what is the statement? What time is it? 40. Okay, 8. I had to think. Okay. Okay. Now, suppose you have a Q-manifold, a general Q-manifold. Let's take M Q, a Q-manifold. So what you can do, you can just suppose you consider a point in the zero locus of this Q field. So let's take a point P. And okay, this is also confusing for me sometimes, but I guess when I'm talking about points here, I'm referring to the underlying topological space. Sometimes I differentiate it, I make the distinction between the graded manifold and the underlying. I use the curly n to refer to this guy and normal m to the base. Okay, so I take a point in the locus of Q. And what I can do now is to consider like some Taylor expansion of the Q field around this point. So we consider coordinates. Yeah. So let's take coordinates around this point. And you know, as Rudolf was saying, this is horrible because you can have this, you know, you can have like odd variables and even variables, and it can be very complicated. But I'm just denoting this by the same letters. But you know that some of them can be anti-commutative and all. Yeah. But I don't care. Okay, so I just take coordinates around this point P. And I consider this expansion, some Taylor expansion, and we will have that this is going to start from 1 because the 0 term is vanishing. This is in the locus, so I will have something like this. Then I have the derivatives. I have the Taylor coefficients. So I will write this. How do I do this? Okay. Just something. Okay, I have some expression like that. How is it going so far? Okay, it's not too bad. Is it bad? Okay. The component, the eighth component of the Q field.
Maybe just very briefly, if to see if I understood this. So you said if you start with an L infinity algebra, you can always understand this as a Q manifold where your topological space is just 0, just one point. And now you're doing something similar, but starting with any Q manifold.
Yeah. Okay, what I want to do now is that you have a vector space. You can see it as a Q manifold, like a very simple Q manifold. But it can also be in the other way around. You can start from a general Q manifold, and you can linearize it, take the tangent space at a given point, and this will be an L infinity algebra. And this is what I want to do now. I think I'm just saying, I'm not saying where I'm going, sorry, but this is what I want to do. I have a complicated Q manifold now. I want to fix this point, consider the tangent vector space, TPM, and this will be an L infinity algebra. And the brackets will be given by this Taylor. They will come from these Taylor coefficients of the homological vector field. Okay? So now the problem is the following. So you just pick some coordinates and you define this L infinity algebra by these Taylor coefficients. But what if you change the coordinates? Or what if you take a point which is not in the 0 locus? So how can you globalize this construction? You know, the problem is to define an L infinity algebra in the sections of Tm. That's the problem that I want to solve. Okay, so there are two answers as far as I know. One, which I hope with all my heart is correct, because one answer is the one that I gave in my thesis. And the other answer was given in some paper by some people. And the structures are different, and I don't know if they are quisomorphic or related in some way, but they look different. And this is what I want to say, okay? Yeah. Okay, so let's take Q-manifold, let's take a point, consider coordinates. Okay, then, okay, we'll just say we can define an L infinity algebra on TPM by using this the Taylor coefficients. But you know that this Taylor coefficients don't behave well under changes of coordinates, as I was saying. So now I will state the problem. The problem is just how to define now problem. How to construct an L infinity algebra on sections of Tm. So you want to define these brackets, lambda k, given here, in a way that they satisfy these generalized Jacobi identities. And okay, I'm not sure about the shiftings here, but probably if I write it like this, they should be symmetric or anti-symmetric. Well, such that this collection satisfy generalized Jacobi identity. Okay. So now the main theorem. I will just say the theorem, and I won't erase this because this is really important. So it's going to be here in the center of these boards. Okay. So I will write how I solve this problem. So wet. Yeah. Okay.
Statement
Mhm.
from where
Mhm.
so the correspondence proof by Akasha went between Q-manifolds and the algebras. So that means that now you're trying to take a tangent space to the corresponding the algebroid and basically look at the point as a tangent space when first jet is zero jet is over the anchor map is vanishing, and you want to make Allen pieces there, right?
I don't know. I think I have never translated this into the algebroids problem. I know this result by Weintraub, and he also commented about this, but I don't know. Okay. Yeah. Okay. So now the main theorem to solve this problem. What time is it? Okay. So I found this in a paper by Voronov. And it's as follows. Suppose you have a Lie superalgebra. Let's L. What? Fyodor. He's in Manchester. Yeah. You know him. He was my teacher. Yeah. Okay. Okay, let's L be a Lie superalgebra. But someone told me that there is a more general version of this theorem, and I didn't understand what this person was saying. Okay, but anyway, I use this because I gave a talk in October about, I was trying to speak about this, and for this person it was like, this is so trivial. And this is there is a more general result, and I didn't know. I was, okay, never mind. I don't know because, but it's a big name, I guess. Okay. Okay, let's L be a Lie superalgebra, and it was recorded. Okay. Okay, let's L be a Lie superalgebra, and suppose you have an abelian subalgebra A inside this L. Okay, so what else? Suppose that you have some projection from L to A. Suppose there exists a projection P from L to A such that the following property holds. So you have something like this, P, okay, AB is P, PAB plus PA, PB. Okay, so you have this bigger L, you have an abelian inside L, you have projection, something more is needed here. Suppose you also have, there is an nilpotent odd element delta in L. Then with all these conditions, you will have that there exists an L infinity algebra on A, such that the brackets are given by the following formulas. So there is an important element. Then there is a L infinity structure on A given by, you define the brackets by this formula, lambda k of A1, AK. They are given by these iterations of this commutator. So you first compute this nilpotent odd element with A1. You compute this bracket, then with A2, and so on until you finish in AK. And then again, you have that the generalized Jacobi identity for this lambda case will come from the fact that this delta square is 0. Okay, so this is very important. This is the theorem that I will use to prove my statement. So you know that I want to define an L infinity algebra on these sections of the tangent bundle. So this will be my A. I need to see the sections of Tm as an abelian subalgebra A inside a bigger Lie superalgebra. So there are many questions that we need to solve. The first one is what is going to be L in my case? What is going to be delta, and how to define this bracket and all, okay? So I will solve these questions now, but I need to erase them. Okay, I don't know. Vinograd? What did you say? How do you write this? Duflo. Okay, but Duflo, I know. Are you feeling tired? Boring. This is boring. I have like 20 minutes. Yeah, okay. Okay. Mm-hmm. Mm-hmm.
I to take these iterative brackets, then I don't see why it doesn't A. But if you have this unlucky.
Sorry, I didn't understand the question.
So I don't see why this iterative bracket should be in A.
Ah, okay, in A. Ah, you're right. Sorry. Okay, I forgot. You have to apply the projection here. Yeah. And of course, it should play some role, this P. Yeah, okay. Thank you. Now. I need to tell you what is L, as I was saying, what is delta. So let's try to do this. So I will try, let me first introduce something that I call formal functions on Tm. Let's introduce formal functions on Tm. And by this I mean the following. So you consider sections of the following bundle. So these are sections of S hat. This is the symmetric completion, so I'm working with formal power series. So I will consider this. Let me just, to clarify this, let me just introduce coordinates, local coordinates on Tm. So let's, local coordinates. X1 till Xn. And then you know that this induces on local frame. You have this del Xi. So again, like corresponding to this frame, to this basis in the tangent space associated at a given point, you will have coordinates corresponding to this basis. So I will denote these coordinates by y's, yi, yn. Okay. So you know that locally you will have that this, if you take around some point and you think locally, you can have these coordinates in this way. Now, what I mean by a section of this bundle is just something that looks like as follows. Now, a section A looks like some expression in this way. As I told you before, you have formal power series. This is a multi-index. I have something like this. And this This coefficient is just a function associated to the base manifold M. Okay, and let me write something. This I is just a multi-index. We can write something like that. And by this yi is just products. Okay, so I have y1 to the power of this first index multiplied by yn to this power. So you have this formal power series with respect to this fiber coordinate. Okay, so this is what I mean by a formal function on Tm. And then what I'm going to do is to consider derivations of these functions. So this is what is called a formal vector field. And these derivations of these functions is what I'm going to use as L. This is going to be my Lie superalgebra. Okay, so now let me use this part. I think it's now consider L as derivations of these formal functions. This thing. Now, how does an element in L looks like? You can write it like this. An element X in this L can be written in the following form. So we can write something like this. X is something like X I, X Y, and this is just a formal function, a section of this bundle. So these are derivations of these type of functions. You have like the Lie bracket, as you just take directional derivatives in between two vectors. This is going to be my bracket in L. So this defines Lie superalgebra. And now what I want to do is I would like to see gamma of Tm as an abelian subalgebra inside here. So I make an identification. Let's consider gamma Tm as an abelian subalgebra of L. So what I do here is that if I take a vector field on M, this can be written as an expression like this, right? And this depends on X. But I make an identification and I write something like this. Okay, and then of course, if you compute the bracket between elements of this type, you will have that this is 0, because the function here, the coefficient function, is independent on y. Okay, how is it going so far? Yeah, I think this is some vertical. This is a vertical vector field associated to, I think. Okay, well, I'm not going to say this, but yeah.
Question. So all of these things like the formal functions and like vector fields on them, you just you wrote down on local charts. Is there any problem to like sheafify this stuff? Because in principle, I think all of this should happen on the level of sheaves, right?
Yeah.
I mean, probably there's just some technical things
Yeah,
happening, but I mean, I can somehow see that it's fine to just look at this locally, and then everything should be well defined. Okay.
Thank you. Okay, so now this is my abelian subalgebra A. Inside this L, and now, okay, also the second main theorem of this construction is because I want to define this delta nilpotent operator. So this is important. Now we need to produce this delta inside L. And I need this to be nilpotent. And I also, okay, I didn't say this before, but you know that you have some projection map from L to A. I would like to have this condition. I would like to obtain that the projection of this delta is just the homological vector field on M. So to produce this operation, we need to use methods similar to Fedosov deformation. So here is where this story connects with deformation quantization. But I decided not to give details of these proofs. I'm just going to say the theorem because it's just too much. So the second main theorem here is this. I want to start, I will take a connection on TM, just on TM, and I will leave this connection to these bundles that I'm using here. So I would like to produce the connection on these formal functions and on derivations of these formal functions. That's what I want to do. Let me write the statement. Okay, the statement is this. Suppose you pick a torsion-free connection. On TM. Then there exists a unique one form. I'm going to write this like this, gamma or R with values in these formal functions on TM twisted by, okay, I'll just write this, such that okay, there is something that I didn't say, but it was important before stating this theorem. Okay, I will write the form that this new connection will have, and I will explain later what I mean by this, because I forgot to introduce some notation. Let me just write it. I will say what is this. So you start from a connection nabla, and you deform this connection to another one, which has values in this bundle, and then you will have that this is nilpotent. And there is an additional condition. There is another operator besides this delta. There is another operator that it has to kill this R. So I haven't told you what is this delta and H. So this delta, it acts as follows. You have some section of this bundle that I'm working with. You do this. Okay, and this H is like the opposite. So here you are increasing the degree with respect to the differential form, and you are reducing the polynomial part. And this h is doing the opposite. So you will decrease the differential form part, and you will increase the polynomial. So this will be defined as yi. There is a contraction of the differential form with values in this bundle. Maybe there is. This is another operator, but h is defined in this way. Okay. This part is horrible. Sorry. This m and this k, they just means that m is the polynomial part and k is the differential form degree. Okay, so these operators that I defined here, they also appear in this deformation quantization in the classical case for symplectic manifolds, and also this condition here that you can modify a given connection to an nilpotent one. These are things that appear in deformation theory. So what I basically did is to try to mimic the proofs, but adapted to these bundles that I'm working here now. But it's just the same ideas that you use in Fedosov method. Okay, so now this connection that I introduced is a connection on the space of formal functions on Tm. Now you can, when you have a connection in some bundle, you can use the endomorphism connection. So you can lift this to a connection on this space of vector fields. That's what I'm going to do now. And then I'm about to finish. There is another theorem. Okay, let me write it here. There is a correspondence between the abelian subalgebra A, which was identified with comma Tn, and formal vector fields X such that let me denote this by D0. Okay, so now I have some lifting map. So I take a vector field on M. I identify this with A by this formula here. And now I can prove that there is some correspondence between the vector field that you start with and some lifting. So you can associate to this vector field, you can associate a vector field on L, on the bigger algebra, that commutes with D0. So now, by applying this theorem, you can apply this statement to the homological vector field Q. So then, for Q, we produce a formal vector field Q hat such that, okay, I forgot to write this projection map. Okay, anyway, it's not so important. I produce this Q hat such that Q hat squared is 0, and it projects to Q. And precisely this lifting of Q, this Q hat, is going to be this delta from the proposition. Okay? So now I computed the brackets, the L infinity brackets, and I checked these identities for the first cases because I didn't know how to write a more general proof. I will give you the expressions for these brackets, and I think I will finish. Yeah, it is too much. Okay. Now I apply this. I have some formulas, but I'm not okay. Anyway, the brackets are given by this. Okay, I obtained that lambda 1, which it takes a vector field and produces a vector field. I produce something like that. I had, okay, you know that this, by this prescription, this should be this thing. And what this gave me, it was something like this. This is what I obtained. Then I had this lambda 2. Yes, this delta, as I was saying, this is Q hat. Yeah. And it produced me this. And you know the other solution that was given by Pinshu, they had almost the same term, but they have the other, you know, like in addition to this term, they have the other part, so they have the Lie derivative along Q. And I only have this term. So I don't know. I don't know what these people did. Okay. I think I was thinking about giving you this, but okay, I am not telling you what it is. Because I saw the formula and I think it's not giving anything, like it's just some random expression, I don't know. But in the case for these people, they have like lambda 2. It's a well-known characteristic class. It's like the Atiyah cycle. And I don't know, in my case, is something very different. I will just tell you that I computed this. But for me, it's no point writing the formulas, but I computed this in my thesis. Okay, I think that's all what I wanted to say.
Well, it's a nice talk. Are there some questions?
What will not work if we will not have a connection? So what we will not able to leave? So if you will just work with delta and this gamma guy. And gamma guy.
Without this, you mean?
Without Nabla, yes. Can we play in this game or something will be not lifted?
Okay. Actually, I don't know.
And
I never thought about this.
And the follow-up question, so does you get some L infinity? Is this L infinity depends on this connection or for any torsion free you will have isomorphic guys?
Okay. Let me think. I can just tell you something that I know, and is that at least in the other construction given by these people, they proved that this, for example, this lambda 2 is independent on the connection that you pick.
Yes.
So in that case, it doesn't matter like what connection you take. I think they obtain the same L infinity, or at least they are quasi-isomorphic. That's what I understand from what I have read. But in my case, I don't know. Yeah, I don't know.
Number. So it will be L differential, which is fine. All right, thanks.
thanks for the talk. I just wanted to ask about was the difference between the formal functions on dm and like regular functions on d star m graded functions, right? Because the coordinate expression over there, it just looks like you take a function on t star m, just reshuffle it around to isolate the y terms.
You mean, okay, you mean like what's the difference between this and C infinity?
C infinity on
star?
t star m, yeah.
Okay. I don't know if this, okay, I don't know if this is like a subset of what you are saying. I'm not sure, okay. But I decided to work with this formal power series.
Sure. So the completion of the symmetric power, does it mean that the y's commute always, or just graded commute?
Yeah, I'm using this graded condition,
Graded commute.
the graded symmetric condition, the commutativity.
You have some formal power series, isn't they not necessarily converge?
No.
That's the difference.
No, but it never does, right? If you take just like functions or graded functions on t star m, those would be formal power series in x's and y's, and then you can just reshuffle it, take the part with x's for each y, just keep the y, put all the x's together, and that gives you like a formal power series in x's, which is a function on m, and then it looks like that, I think.
Okay, well, I don't know.
Okay, never mind. Thank you.
These are variable set.
I don't think it needs to.
Maybe I can also ask a small question. So I understand that you want to like use this theorem here on the top blackboard, Voronov. And so I didn't really understand what the projection map was. So you say you take as your L, this was like derivations that have as coefficients this in x and y.
But you can set this variable here to be 0. And then you will project to this abelian subalgebra. This is the projection map. But I didn't give it. Yeah.
But if you have the partial y's, and then you simply say, okay, you take no.
No, what I mean is that you can just like in these coefficients, you forget about this part. Like
Okay,
whenever
so
you have
you simply
like you
restrict
just take the C infinity m part in this coefficient, and that's all you do.
Okay, so you simply restrict this part to only the x coordinates, and then you see, okay, all of the Lie brackets vanish. So okay, this is okay, makes sense.
Yeah.
Okay, thanks.
I mean, I hope so.
Hope so. Okay, are there more questions? Maybe from some of the online people. If you have a question, feel free to simply unmute yourself and ask the question.
Yeah, I was a bit confused. The Q hat is the Duflo, let's say Duflo Nabla. I mean triangle. The Q hat, do you hear me?
Yeah, I can hear you.
Q hat was the existing triangle from the theorem of Voronov. Or this is a question. Yeah, so
this
Q hat triangle.
is delta. Is this triangle
Okay,
from
so
the
this
theorem.
Q hat was related to delta from the theorem, yeah? Thank you. I was not sure because I was teaching along, so thank you. I was interrupted. Thanks.
More questions?
If not, let's thank the speaker again. And just a little advertisement. So next week we will have Jakub Kuda who is going to give a talk about C-star super rigidity of virtually abelian groups and Cartan subalgebras. So see you next week.